today we're going to be learning about electricity. We learned about electric fields, we learned about magnetic fields, we've also done electromagnetic waves and so forth, but let's actually learn about electricity. So, you're probably already familiar with some electricity. We saw that current, so current, represented by the letter I, is a measure of charge per second. I just put T. So how many charges are actually going through a single point ever so much time units? So if we have a wire, then we have some charges going through it in some direction. And if we look and we're over here watching and we count 1 coulomb of charges per 1 second, we get 1 ampere of current. Ampere is usually abbreviated as amp and has just the letter A. The current is usually measured in amperes, which is often abbreviated as amps. Charge is measured in coulombs, and time is usually in seconds. We won't be using this too much, as we don't really care about how many charges are going through, as that's irrelevant. We have voltage. Voltage are voltage difference, or other names for voltage. Voltage has a lot of different names. Potential difference. This would be electrical or electric potential difference. Voltage drop. Potential drop. Electromotive force. I'm going to put asterisk by this. Which electromagnetic force is abbreviated as EMF. There's a lot of names for voltage, and they all, except for electromotive force, reference the same thing. There is a very subtle difference between EMF and voltage. But even if you, I'm looking up.
Miss Bambi, come out front office, please.
The voltage, electric potential difference, electromagnetic force, electric pressure, electric tension is the difference in electrical potential between 2 points. Is defined as the work needed per unit of charge to move a test charge between 2 points. It's related to the potential energy. If you take a bowling ball and raise it 10 meters in the air, you give it gravitational potential energy. You take a electron and you put it in an electrical field, it's going to have a potential energy to want to move from one point to the other. The difference between voltage and EMF, though, is EMF is perfect, while voltage usually refers to real world. So, for example, let's say we have a perfect battery. And we'll see the symbol. This is a symbol for a battery. This is a perfect battery. A battery is going to have some resistance to it, and resistance prevents the flow of current. So inside of a battery, you have some resistance and some voltage source. This would create, right here, a voltage. If you measured these two terminals right here, there would be a voltage difference. So if this was a 3 volt, or this is a, what is AA batteries, 1.5 volts? This is a AA battery. Then the positive terminal, the negative terminal here, this would be 1.5 volts. This will be 0 volts. The voltage difference between here and here is 1.5 volts. However, this right here is your EMF. If your resistor right here was zero resistance, your voltage source would have an internal 1.5 volts here. But this is what creates the voltage. So that's a very subtle difference. EMF refers to the actual mechanical system internally that is creating the voltage. So you can always look at 2 points in a random circuit and find a voltage difference. You can look, it doesn't matter if this was 1,000 volts and this was 1,001 volts. The voltage difference between here is still 1.5 volts. But this would obviously no longer be an EMF. An EMF is the underlying thing that's creating it. Which brings us to Ohm's law. It states that current is equal to voltage over resistance. So current is equal to voltage over resistance. I never memorize that. I instead do the alternative definition, VIR. Voltage is equal to current times resistance, as I always remember it as VIR. So suppose, let's say, what's the voltage that we use in the building? If you were to go lick the socket, how many volts would go through your tongue? What? You don't work. A 120 volts. However, note this is AC, alternating current. It's constantly going from, the current is constantly switching. So it's constantly turning on and off. It looks like this. So if you look at the current going through it, it would be perfect. Your current it gradually drops down to 0, and then it reverses direction. So it's constantly building up, getting stronger and stronger in one direction, then slows down and turns off, and then actually flips direction. Whereas DC, so this is alternating current, DC would be something like this, versus a straight line at one Yeah, direct. It doesn't change. And let's look up a space heater. So space heaters usually draw around 12.5 amps. Will be the resistance inside the, and this is going to be like the max peak of it, peak amps. What will be the resistance of it? So resistance is equal to voltage over current. So that'd be 120 volts divided by 12.5 amps. And we get 9.6. And what will be the units for resistance? Repeat that? You're close. Ohms. So this is the Greek letter omega. You could write out words, the word if you can't draw it. Always draw it like this. Or alternatively like that. Either way is good. I always put the little tails going up, but this is acceptable too. By the way, how many amps would kill you? .1 amps. So 100 milliamps across your heart is fatal. It would short circuit and cause your heart to squeeze in on itself, and then it wouldn't be able to start again. Which is a crazy small number. Again, it has to go across your heart. When working on high level stuff, it's called the one hand rule. You put one of your hands in your pocket and you work one handed on your electrical system. As if you accidentally touch ground, then touch a live hot thing, the only pathway is through your heart. As if your ground is your feet, you touch it with your right hand, it's going to go through your blood, as blood is going to be the least resistive way. Your skin has high resistive, your nervous tissue has low, but it's mostly going to be going through your blood supply. As it goes down one side, it will not go through the heart, but instead go down to your leg. So, what is current? Actually, what is it moving? What type of charges? So it could be either. What do you think it is conventionally? Positive or negative? Why? Did I tell you about this before? Oh, did you do this before? You are right. Conventional current is assumed to be positive charges moving. So you have to remember history. Benjamin Franklin doing his kite experiments, studying electricity. At that time, we didn't know what an atom was. We didn't know what an electron was. We had no clue what these charges were, but we do know what charge is. and there was no way of capturing a bolt of lightning and seeing whether it was positive or negative. So he guessed. So, well, I like positive. Just assume it's positive. And what happens whenever you make a standard? Even if it's a bad standard, it will persist for all eternity almost. It's one of the reasons why computers and and a lot of things are extremely horribly written and used, is because once something is created and it catches on, regardless if it's the best thing ever or the worst thing ever, that's what we're going to use from now on. The layout of the operating system, how things were done in the computer. Every time we release a new operating system, all we do is slightly change the previous one. We would have to completely redo the entire computer systems, and then no software will work on it. So they're like, well, we can't have that. We have to be able to use all the old apps on your phone. We can't just tell everyone, sorry, but all your apps are going to be deleted. No one will buy the new phone if you can't use any apps on it yet. So they have to support all the previous stuff, which leads to wrong things, but we assumed is positive, which in physics makes no difference. A positive charge moving to the right, how can you, so if you have a negative 1, so if we have, for example, let's say we have a +1 pointed in this direction. Remember vectors? Or I should say, let's have a -1. You can flip the direction and change the sign to make them equal. So having a plus charge going to the right is the same thing as having a negative charge move to the left. These two things are the same thing. So in a battery, we have the positive terminal here and the negative terminal here. Conventional current, which is I, will flow out of the positive terminal and go around to the negative terminal. This is what we're going to define as current. In actuality, current is negative electrons that come out of the negative terminal and flow in the opposite direction. So it's important to know that conventional current is opposite in sign, i.e. positive, and opposite in direction to the actual flow of electrons. So some circuit notation. This symbol is called a cell, a battery, or voltage source. There are some. These can be used for battery or voltage source. The proper name is cell. This would be a multi-cell. It's just two cells put it together. It's also a battery and a voltage source. And you could even have, as long as you want it to. This would have 3 cells in it. You'll see this and this used a lot. It makes no difference. They're the same thing. So the short side is the negative terminal. The long side is the positive terminal. So that means current is going to flow out of the bigger side. In America, we use this symbol for a resistor. A resistor provides electrical resistance to the flow of current. It resists current. We also have this symbol right here. This is known as a switch. You can think of it as you flipping this down and completing the circuit. You will see this often, and usually I'll say, in case I forget, assume the switch is closed. Because usually it's going to ask what happens when the switch is closed, what will be the current at this point. So let's suppose we have a 12-volt battery. And the amount of squiggly lines doesn't matter. In European and other notations, they have a single box, which I think is kind of better, but I've never used it. Because that means you can write the ohms inside the box. Let's make this 6 ohms. What is the current coming out of this battery? So current will come out of this side. What would I be? Alright. So current is equal to voltage over resistance. That'd be 12 volts divided by 6 ohms. And that would be 2 amps. Alright. What would it be now? I have 2 resistors in series. So when things are connected in series, meaning that the current flowing, you can think of this as a black box, the current flowing through it doesn't branch off anywhere. then we have this equation. So if you have R1, R2, Rn, then the equivalent resistance would simply be R1 plus R2 plus ... Rn. You just add them together. So these two resistors can be replaced with a single resistor of 6 plus 6 are 12 ohms. And then we have current is equal to 12 volts over 6 ohms. And 12 ohms, which would give you 1 amp. What would be the current of this battery? Good guess though. I mean, if you had calculus and or maybe did a lot of algebra, maybe. But there's a new rule for parallel. So these resistors are in parallel. They share the same endpoints. You can connect this one to this one without passing through any other resistors. You can connect this one and this one, so they share the same wires. This is being called in parallel. So if you have R1, R2, Rn, so they're all connected without anything in between them, all in parallel. So this is for series, this is for parallel. Then R equivalent, these all can be replaced with a single resistor, Req, that will be equal to 1 divided by R1 plus 1 divided by R2 plus ... plus 1 over Rn. Technically, this is defined as 1 over Req equal to 1 over R1 plus 1 over R2 plus ... plus 1 over Rn. But this solves for 1 over Req, solving for this. Do that. So these two resistors has an equivalent resistance of 1 over 6 plus 1 over 6. 1 over 6 and 1 over 6 gives you 1 over 2/6. Dividing by the fraction is the same thing as multiplying by the reciprocal, so 1 times 6 over 2. And that will be equal to 3 ohms. So this is equivalent to a circuit that is connected to a 3 ohm resistor. So our current would be equal to 12 volts over 3 ohms, or 4 amps. But so adding in parallel actually decreases the resistance, which makes sense. Current can either go down this path, but if there's too much resistance here, or if it encounters any resistance at all, some of it can start now going down this. So it has two paths to choose through. Imagine you have a highway that splits off into two different paths. If this one starts getting congested, you could take the less congested path. And if they all eventually reach the same endpoint, then you have two different paths you can go. Or think of it as a 4-lane highway. You can choose the left lane or the right lane. Volt battery. 5 ohm, or let's do 8. 8 ohm. I start getting messy whenever I keep adding the tells, which is why I usually drop them. Alright, how much current is going out of this battery? So what would you do first?
You do the series of resistance first.
Which two are in series?
The
Which top 8? This one? What's it in series with? So remember, to be in series, let's say, look at these two right here. Current has to go through it without branching off. There's a branch in between them, so these two can't be in series. To be in parallel, two things must share the same two wires without going through anything else. So, for example, these two share the same wire here, but this one has this wire and that has that wire, so it's not the same two sets. If you can connect, if you can go from one terminal to the other, and then from the other terminal to the other terminal without passing through any resistors, it's parallel. So the key trick to this problem is find something in series and find something in parallel and simplify it down. So what's something in series and what's something in parallel? And series is the most easiest, so always look for two things in series first.
series have to be the one like
With no branches between them, so they're connected. So current doesn't divert anywhere. So yeah, so the top corner, current is going in this direction, and then enters this one. It never diverged or went everywhere. So these two are in series. So we can replace it with a single resistor. So we have 8 ohms, 8 ohms. So it's connected right here and right here, so we can replace it with a new resistor. What would its value be? 16, so they just sum. Alright, what things are in series and parallel now? Which one? This one and this one? This one? Right. So this one right here? The one above it? So we can connect it right here, but then when I try to connect it right here, I pass through the battery, and when I go through this way, I pass through this one. So there's no way to get to this side of the battery. I mean, we can connect these two right here, obviously, as there's a straight path, but there's no way to go from this terminal to that terminal without passing through something. So let's cover all. Do any two resistors share the same two colors? So this one and this one? So yes, you can go from here without passing through any single other resistor. You can go from here to here without passing through any resistor. So at this point right here and this point right here, we can replace this with a single resistor. And to solve for it, we have 1 over 1 over 8 plus 1 over 16. You can plug into the calculator, or you can do this by algebra. I'm not algebra, this is just common math. So that is 1 over 3 over 16, which is 16 over 3, which is going to give me so 5.3 carried. All right, now we'll reduce. On this one, we reduced these two are in parallel. These two are in series. And you can see these are in parallel because they share the same colored wires. So what do we reduce now? The bell's about to ring. So looking at this one, there's no branches right here. So this would be in series. So 8 plus 5.3 is 13.3 carried. These two would now be in parallel. They can be connected like that without passing through anything. So you do 1 over 8 plus 1 over 13.3 carried. Just plug that into the calculator. Make sure you put parentheses on the denominator when typing it into a calculator. So that's equal to 5. So that's 5, that's 8. 8 plus 5 is 13, so that's equivalent to a battery connected to a 13 ohm resistor. And now we have one resistor, one voltage source. The current is equal to voltage over resistance. That'd be 10 volts over 13 ohms. And that gives you 0.769 amps. Make sense?
Go slow.